Thank you all for having me. It's a great pleasure. I hear a lot about Optima, even here in Europe. So it seems to be an amazing network, and yeah, great pleasure to be here. So yeah, I mean, my main research is in black box optimization. So I put a little word cloud on the top right of the slide just to share a little bit what I typically do. And this presentation is not about any of that, what I typically do, but it's about some other topic that I consider a hobby. And it has been a hobby for me since my master thesis, essentially, or diploma thesis, as we call it in Germany. And it's a topic I share a great passion for. I see a lot of potential, and it's coming back to me every now and then. And at the moment, there's a lot of momentum, a lot of nice research questions, and I thought it would be nice to share a little bit with you guys, because I believe that there's a lot to be done, and hope that some of you will find it inspiring. And I should also say that, I mean, I cannot see you because I only have this one screen. I'm like currently speaking from home, so I don't have an external screen. I can't see your videos. If you have questions, please just unmute yourself and jump in and interrupt me. I'll be happy to take questions all along the way. Okay, with this, yeah, let me get started. So I will explain everything. I mean, don't worry if you don't know star discrepancy. If it's the first time you see it, we'll go introduce all the concepts very smoothly. And anyway, this talk is not going to be very technical. So I hope. Let me know at the end whether I succeeded. Maybe this slide just for reference. These are like the key references for the presentation. All of this is based on joint work with François Clément, who's a postdoc now at the University of Washington and who did the PhD with me at Sorbonne University and with Louis Paquet at the University of Coimbra. And we had Catherine Klamroth joining us halfway through the project, and she brought a lot of momentum to this whole research. And you can see, I mean, the kind of main papers, two main references, one of them published as a brief report in Proceedings of the National Academy of Science, and the other paper published in the Proceedings of the American Mathematical Society. So there's quite some kind of momentum for this research, as I mentioned. I believe that some of the findings are interesting, or an interesting starting point, essentially, for what has been a topic, star discrepancy optimization. It has been around for more than 100 years. And I also want to share that this is not only, I mean, obviously most of this work is inspired by this work with François, but there's also a lot of like ongoing work with Martin Durand, who is a postdoc in our team. And we were joined by a high school student, Noam, who worked with us on this topic for 2 weeks during an internship. And Doerr, who was a bachelor student at the time, now master student at Oxford, who joined us for this project as well. And I'm sharing that to show to you that none of this requires like years of study, but it's more about having a cool idea and a nice vision, and you can contribute to this kind of research. And since I know that there are many students also attending these Optima series presentations, I thought it would be interesting perhaps to share that, that there's room actually to get involved and to bring in your own contributions. So what is star discrepancy optimization about? So it's all about placing endpoints as uniformly as possible. And to make it easy for us, we will always consider the d-dimensional hypercube. I don't know, I hope you don't see this. Yeah. So we will always work in 0, 1 to the d-dimensional hypercube. And if I ask you to place endpoints as uniformly as possible on a line, then, and I gave you 2 minutes, then I guess most of you and even high school students would possibly come up with a design like this. So we place these points like that. And indeed, I mean, arguably, this is pretty uniformly distributed. When we go to 2D, then already the question becomes way more complex. So look at these 2 point sets and tell me which one do you think has a better distribution or is more uniformly distributed. And now we need to argue, right? I mean, I believe that many of you would probably favor the design on the right over the design on the left. But if I ask you why is that the case, then I don't know. Then you would probably tell me about that there is a fewer kind of parts where we do not have any points. The points are here. We have some clustered points, which we have far less here in this picture, and so on. But so we need to kind of justify why we believe that this point set is more uniformly distributed than this one. And there are many, many different ways in which we can characterize or measure how uniformly a point set is distributed. And one of the characteristics that this whole discrepancy theory is about is that we take some objects, like this one, for example, and what we want is that the fraction of the points that are inside this this object corresponds roughly to the volume. So remember, we are in 0, 1 to the d, sorry, 0, 1 to the d. And so if this volume here, for example, is like, what is it? Less than a fourth, maybe it's a 1/6, then we want 1/6 of the points to be inside this little shape, okay? And we could do that for all sorts of shapes. So for example, we could look at circles and say, okay, for all possible circles, we would want that the fraction of the points approximate the volume of that circle. And one notion that is particularly famous and well studied in this whole discrepancy theory community is the star discrepancy. And why star discrepancy? Star, because essentially what we will do is we will always look at rectangles that are like parallel, so no rotation at all. We will always look at parallel rectangles, and all of them will be anchored in the origin in 0, 0. And we will come back to this question. I mean, you may say, but why should we anchor them in 0, 0? We will come back to this question later. But for now, maybe we can just accept that this is what we care about. Is we care about rectangles of this shape, of this form. And what we want is, again, we want that the volume of such rectangles. So here, for example, we have like 0.5 times 0.6. So this volume. And we want this volume to be approximated by the fraction of the points that fall inside. I hope that this is kind of like the intuition is clear. So this is how we will measure how uniform the point set is. And then we will just change, and we will want that, like, this volume to be approximated by the fraction of points for all possible rectangles that are of this shape, that are anchored in the origin and parallel to the coordinates. So we will have to look at this rectangle, and so on. And now, in order to make it a formal, I mean, it's one of the very few slides where I have actually formulas. We can define the local discrepancy in this point Q. So this point Q here is the upper right corner of the rectangle. And we can look at this rectangle, and we will look at the volume of this box. So in this case, 0.9 times 0.4. This is the volume. And then we will look at the fraction of the points that are inside. So this is just the number of the points inside this rectangle. And we look at this fraction. And we want the two of them to be close, and we measure the absolute difference. And this is what we will call the local discrepancy in this point Q that defines the upper right corner. And when we have defined this local discrepancy, then what we could do is we could go and we could average, right? We could say that, okay, we want for all rectangles to be this approximation to be as tight as possible. And we can measure that according to different norms. And why not take the P norm? And in which case we would just average over all possible upper right corners Q. So we would move around Q, we would get different rectangle for every possible point Q, and we would then just take the P norm of these local discrepancies that we just defined. And one notion that is particularly well studied is this L infinity star discrepancy. So we look at the infinity norm, which is just that we look at the worst discrepancy, the worst difference, absolute difference between volume and the fraction of the points. Yeah. And what we would want now, yeah, is that this discrepancy is as small as possible. Yeah. So the smaller this discrepancy, the more uniformly the points are distributed. I hope that this is clear. I don't know, maybe I should stop for a second and see if there are any questions.
I have a question, Carola. Yeah, sure. I would have, when you first asked how to measure the uniformity, I would have assumed you'd be going for an approach of like looking at minimizing the standard deviation of the distances between pairs of points, but you haven't chosen that. Is that because you're concerned about computational cost of measuring this?
No, okay. So there are other measures like dispersion type measures that look at more at pairwise distances between points. It's a completely different story. I will come to the motivation of these discrepancy notions second, why we study them. But I mean, one thing to keep in mind already is that actually computing these discrepancies is extremely hard. So in particular for the star, in particular for the star discrepancy, for the L infinity star discrepancy, we know that this is an NP hard problem to compute. So it's not about computational efficiency. It's really more. I mean, let me show you the next slide to motivate why people are interested in this kind of strange notion that looks a little bit weird with these rectangles.
Thank you.
Where does it come from? So why are people excited? I mean, I should say that there's a lot of research about this L infinity star discrepancy, and maybe I wanted to show it later, but maybe I should mention already, if you have heard about Sobol sequences or Holton or Four or other point sequences, they all come from this community that studies star discrepancy or discrepancy theory in general. And so why do people get excited about this star discrepancy? It all goes back to a pretty famous inequality by Koxma and Lafka. So the two of them more or less independently discovered that we can bound the error that we make when we do numerical integration. So imagine we want to compute this integral here, but we do not know how to compute this in closed form. So then many people, I mean, the easiest thing to do would be just some kind of Monte Carlo approximation, right? So we could evaluate this function f in some random points typically. And then if we take, for example, the average as a simple rule, we would want this average to approximate the true integral of the function. And what this Koxma-Lafka inequality tells us is that the absolute error that we make by approximating the integral with this average is bounded from above by these two terms here, by this product. And the first term, if you look at it, the variance of f, that is given, right? I mean, the function f is given, there's nothing we can do about it. But the second term here, this is exactly the L infinity star discrepancy of the points in which we evaluate. Yeah? So we completely separate the error that we make, I mean, or at least this upper bound, right? Like the contribution of the function, we cannot change anything, times this discrepancy. And this is something that we can control, right? Because we can control the points in which we evaluate our function. And now, maybe we should mention it right away, is that the funny thing is that, and this whole star discrepancy, like why is there hype, is because people realize that actually we can have smaller discrepancy than just taking random points. And this gives then rise to so-called quasi-Monte Carlo integration rules, where we essentially design point sets here, x1 through xn, that have small star discrepancy, so that we have a small guaranteed error when we of this kind of rules. And that's where the whole excitement comes from, and this is why star discrepancy is like kind of a measure of choice, essentially, to measure uniformity of integration or of distribution in this way. Does that answer your question, Kate? Okay, I hope it's...
Sorry, thanks, yes. Thanks.
Yeah, okay, good. So it all goes back to Koxma-Lafka. I forgot exactly when they proved these bounds. I think it was in the 1930s, something. I hope I'm not too far off. And then there was there's a whole series, as I said, Sobol point sets and so on, that were introduced to essentially minimize this kind of notion. And now this is where optimization comes into play, right? Because now, I mean, when we have this bound, then now we can go and we can say, okay, let's minimize this discrepancy value. And this is exactly what this whole presentation is about. Yeah, is that if we are given a dimension D and we are given a number of points N that we shall place, or that we are allowed here, for example, in which we are allowed to evaluate our function, then what we need to do is we need to place x1 through xn somewhere in this 1 to the d, and this is d-dimensional hypercube, such that this star discrepancy is minimized. Yeah, we want that to be as small as possible. And so this will be the objective for the whole presentation. And there's one other way in which we could look at it. We could also say, and this is interesting, if you want to have a guaranteed error. So for example, imagine that you are whatever you want to integrate. I mean, typical applications here are in financial mathematics, for example. Imagine that you want to price some stock or whatever, some some financial derivatives, then you may also want to say, okay, I want the error, I want to bound the error that I make, and I want this error, I want this discrepancy to be at most epsilon. But then in how many points do I need to evaluate the function so that I'm guaranteed that the discrepancy will be at most epsilon? So this is the so-called inverse star discrepancy problem. We will see that popping up every now and then. So here we fix the dimension and we fix the error epsilon. And what we want is we want to have the smallest n, so the smallest number of points. We want to know how many points do I need so that there exists a point set x1 through xn with discrepancy bounded from above by epsilon. So these are our two main objectives here in the presentation. Okay, so now let's do it, right? Let's go, let's do and minimize star discrepancy in one dimension. And as I said before, I think most of you would come up with a design like that. Even like, I don't know, my 9-year-old son would probably come up with exactly this design if I asked him to place points in the most uniform way that he could possibly do. And indeed, that turns out to be optimal. You cannot do better than that in the one-dimensional case. And then interestingly, in the two-dimensional case, so let's first look at some random designs that people may come up. So maybe my son would probably say, oh, this looks pretty uniform. What I will do is I will, like if I have to place n points, I will place square root of n points, like in the x direction, square root of n points in y dimension, and then I will just look at this grid. But if we look at it, then this grid is actually not very good for this discrepancy notion, because if we look at this rectangle here, for example, right, then it has a certain number of points. And if I just move like this upper right corner by an epsilon to the right, that includes these points that were excluded in the red one, I have now, out of a sudden, I have square root of n more points, but I just increased the volume by an epsilon, right? So this shows that for discrepancy notion, the grid is not good at all. And I think it kind of corresponds also to our intuition that, for example, imagine that you wanted to approximate a function, like, right, imagine you wanted to build a surrogate up on your kind of initial design or design of experiments, as people also refer to this kind of points. Then we typically don't use grids, right? Or maybe people in practice do use grids, but they shouldn't be using grids because the information that we learn is very limited if we do an initial design like this. Okay, what people often do is they take uniformly sampled points, IID uniform sampling. But if you do that, then actually what you can show, and it's not too hard using some kind of bounds or whatever, is that you will typically have some regions where you do not have points, and you will have other regions where you happen to have many points. Yeah, just by the fact that we place n points, you look at the probabilities for things to happen, and then it's not very difficult to show that the discrepancy would be kind of in this order. By the way, here in blue, I always put like for the two-dimensional case, and then in gray is like for the general d-dimensional case. And then the whole excitement about low discrepancy is, as I mentioned, that people realize that actually we can do better than just uniform sampling. And if you go back to this question of integrating the function, we can do better than Monte Carlo integration. We can do quasi-Monte Carlo integration, and we can use these low discrepancy point sets like this one. And we call a point set low discrepancy if the discrepancy that we measure is of this order. In 2D, it can be as low as log n divided by n, and in the d-dimensional case, this is kind of an upper bound. So there are constructions that satisfy this kind of discrepancy bound. And this is where the whole excitement comes from, yeah? So it is possible to place points more uniformly than with just uniform sampling. And this is what we call quasi-random point sets. Yeah, so there's random point sets, pseudo-random, but this is quasi-random. Okay. Actually, and this is just for the connoisseurs. If you want to know a bit more, for in 2 dimensions, we know that actually this log n over n is actually tight, so you cannot do better. What we do not know is what is the leading constant here. There's a big question. We'll come back to this question later. And in the d-dimensional case, we have this upper bound here that I mentioned before. and the best lower bound that we had for a long time was essentially log to the d over 2, roughly. So there's like a factor 2 kind of difference. And then there was a big kind of improvement when Dimitri Bilek and others showed actually that there is this plus epsilon in this term here, which was a big improvement for the first time after a long time. But still, that's still where we are at the moment, and nobody really knows, and it's considered to be a big open problem in discrepancy theory, is what is the correct bound. But I'm not going to talk a lot about these bounds. Don't worry if you don't care about these bounds. What we will do instead is we will want to, we will go back to our question, okay, what do these constructions look like, and what can we do from an optimization point of view? And maybe just to give you a little bit of an intuition, or maybe I should ask if there are any questions put here at this point. Maybe not. Then let me just say, what do people typically do? So in one dimension, as I already mentioned, we can place these points as my son would do, right? And as probably all of you would do, and that's great. There's one construction if you want them to be like, we call them sequences, so you want to place them one after the other, and you want to be good uniformly for every possible number of points. Then it turns out that actually if you take an irrational number alpha, and then we look at this kind of the fractional part of I times alpha for the highest point, then this is a so-called low discrepancy sequence. So if you stop it and evaluate it at any n, then you are guaranteed to have kind of low discrepancy. And now what we can do is we can take these one-dimensional constructions and we can kind of lift them to two-dimensional case by just taking essentially the first coordinate, taking this design that my son would have done, this regular one, and then in the y coordinate we would use these kind of construction that are a bit more kind of irregular. And that turns out to be actually pretty good point set, and they guaranteed to have this low discrepancy, so this log n divided by n kind of discrepancy. And one of the most famous example is when we have alpha equal to 1 plus square root of 5 over 2. I think you all know this number, phi, the golden ratio. And then if we do this, then this is a so-called Fibonacci sequence. And here's an example for 128 points. We see it looks kind of regular. It looks a little bit like the grid, but kind of rotated. And it's not quite exactly the grid. But yeah, this is one of the best constructions that we have at the moment for like 2D. Then I already mentioned Sobol and Halton sampling. This is for arbitrary D. This is the best kind of that we have at the moment. If you go talk to people who care about design of experiments, who care about, let's say, who work in Bayesian optimization, where you want to approximate functions with surrogates and so on, they will typically use Sobol sampling because we do have some guarantees here, and it's kind of among the constructions that we have is one of the ones that has the best properties. So even if you have never heard about discrepancy, you may have probably heard about Sobol sampling. And I'll be happy to discuss that later at the end of this book. Okay, so this is what people would do in 2D, but now let's go back to this question. We're optimization people, right? You're optimization, you care about optimization, I care about optimization, that's my original background. So you can ask yourself, okay, but are these constructions optimal, right? And so it's really surprising that not much is known about placing really optimizing this low discrepancy or this discrepancy notion. So before our work, the only results that were known are essentially go back to a paper by White. I think it was some kind of thesis that he did. I don't know whether it was a PhD or a master or whatever thesis. From 77, and what he did is he looked at the two-dimensional case, and for up to 6 points, essentially, he showed how to place them optimally. Yeah, and then there are some proofs that show that you cannot actually get better or smaller discrepancy. And when we want, statements in higher dimensions, 3, 4, 5, 6, 7, then actually it's even more frustrating because all we know is how to place 1 point or how to place 2 points. And even those results are pretty recent if you consider it. And that's where we are. And for optimization people, I mean, if you look, I mean, it took me 3 minutes to explain to you what star discrepancy is and how we define it. And nobody has optimized these kind of notions. And this, again, I mean, coming back to Kate's question, one of the reasons is that computing these discrepancies is pretty difficult, because we need to essentially, for every possible Q, for every possible upper right corner of the rectangles, we need to measure this difference, this absolute difference between the number of points inside the box and this volume. Okay, so here comes our work, and this is like from the first reference, Proceedings of AMS, is that we extended the results. So in 2 dimension, we can compute up to 21 points, in 3 dimension, up to 8 points, which is kind of, I mean, considering that there was no progress since this, and it's quite moderate. We do this, they say, okay, Carola, placing 21 points in 2D doesn't really matter. I agree. I mean, probably the excitement here is not so much in the precise kind of point sets themselves, but what the excitement really is about, I'll come back to the slide in a second, is much more about the structural insight that we gain from looking at these point sets. So what I'm showing here is the Fibonacci point set that I introduced earlier, where we take these kind of fractional parts, phi times I. Here we have a Sobol construction, and here we have our optimized point set. And if you look at this, and what I'm showing here is in these heat maps is like for every point is colored by this local discrepancy of the point that is of the rectangle that is essentially has the upper right corner in this point, for example. I hope you can see my pointer. And if you look at the scale and you see, so this Fibonacci sequence has like the worst, this kind of, this is what we care about, right? It's like this absolute, like the L infinity norm. So we would look at the worst discrepancy, the worst absolute difference between volume and fraction of points. So here we are somewhere around 0.165 maybe for Fibonacci. For Sobol, it's much, much larger. So you see that these constructions are much worse. And for us, it's 0.09 something. Yeah, so quite a big difference compared to the previously best known constructions, Fibonacci. And again, what is more important than just this absolute improvement is that the structural insight, if you look at this, if you look at this, and if you look at this construction on the right, I think we would all agree that this construction on the right looks very different from the constructions on the left. And it becomes even more evident if we kind of crop a little bit the scale, and if we only focus on the regions where we have a big mismatch. And what we see on the left and in the middle is that for Fibonacci and Sobol, we only have such kind of triangles that point to the lower left. Whereas here in our optimal constructions, we do have triangles pointing both ways, right? So we have triangles here that point to the upper right corner, and we have triangles here that point to the lower left. And we also see that if we do the same kind of cropping, then here we have still much, much more regions. We cover a much broader region where we color actually the space. And this is for 2 points. We see exactly the same thing happening for 18 points. And if we do for 21 points, it's exactly the same thing. So we will always have this kind of here, only these triangles pointing this way, whereas here you have triangles both ways, and you see this kind of hyper, yeah, how do you call them? Yeah, like equivolume, kind of like these hyperbolas popping up. Okay, so and this structural insight, so when we showed this to people who have been constructing low discrepancy sequences for a long, long time, I think it kind of was eye-opening for them to see that, and to see that actually, yes, all these like traditional constructions, something is wrong here when we look at this. And so this whole excitement is, I think, is that this hopefully can inspire a completely new kind of the constructions that will have much lower discrepancy than what we had before. And if I'm coming back to this slide here where we compare, so here I mentioned we have results for up to 21 points, and here I put all these numbers. So we have this kind of like the Fibonacci kind of like, which is the competitor, like the best known sequence. Maybe we can see it a little bit better here in this plot. So I'm plotting here the discrepancy for different number of points. And ignore the green curve for a second, sorry about that. But if you look at the orange one, then you see that the discrepancy is much smaller than the one of the Fibonacci. And if we look at this inverse discrepancy question, so for example, let's say for 20 points, when I use the Fibonacci sequence, I can get a discrepancy of 0.1188. So this is this value. And if I look at our optimized constructions, and I can have exactly the same, or even smaller value if I only use 10 points. So instead of 20 points, and instead of 20 evaluations, I only need 10 evaluations. So I cut the number of points that I need to guarantee this error of 0.11 by half. And if you now imagine that you're in whatever, a car manufacturing company, and every evaluation may cost you to crash a car or whatever, or it may require a simulation that runs for a whole weekend, then cutting the budget by half is quite some improvement. And again, you may not care about 2 dimension and 20 points, but I think that the key message here is that there is a lot of potential for us to optimize over. And this whole, this whole domain actually is just, I think, eagerly waiting, I think, for people like us coming and helping them optimize these point sets. And now you may ask, but Carola, this is crazy. I mean, if this is so important, why would people not have studied that? And I think this is, and maybe the key takeaway for me for this whole presentation is that because people never asked themselves this question, because the people who study these low discrepancy kind of settings, they are mathematicians, and they tend to think in asymptotic terms. So they tend to think in terms of sequences, like you're adding points one after the other, and you want asymptotically a good behavior. So remember the formulas that I showed to you before about the discrepancy here, they are all like big O notation, right? So this says something about the asymptotic behavior of what happens if we add more points. But in reality, we don't care about that, right? We don't need, like for an infinite number of points, we don't care what happens. If I'm in this car manufacturing company, I know that I only have this one weekend to run my experiments or my simulations, and I have to live with whatever number of evaluations I could do. Or if I want to price my financial, whatever, derivatives products, then I know that I only have this much data. And so there's a complete mismatch, essentially, between like this mathematical question of what happens in the asymptotic case and the, like, say, real world question, or maybe computer science question of what can I actually achieve if I'm fixing the number of points, if I have a given budget of evaluations. And I think it's I think the key innovation that we brought essentially to this domain is that we actually go and we ask this question, and then we go and optimize over this. We obtain these results, and I think for many people it was a big surprise and an eye-opener to see, look, wow, there is really a lot of potential there. So let's now go and try to really see it as an optimization problem, and to see what we can do for them. Okay. So how do we do that? So we use NLP. Usually I try to make a joke. People think of NLP, they think natural language processing, but actually for you guys, it's no surprise, NLP, nonlinear programming. So that's all we do. Essentially, we use Gurobi to solve our problems. We could have used other solvers. For some reason, we happen to use Gurobi. Of course, it's not as simple as that. Unfortunately, there is a few, like we also had fun, like proving some lower bounds that help us kind of cut the model short. Some statements about how these points would relate to each other, so that we can prove that there are always optimal configurations where no 2 points share a coordinate. That's what we call the so-called general position kind of requirement. So there is a little bit of, like, to say, technical mathematical techniques that go into these results, but the key technique really is this NLP, nonlinear programming, which I hope many of you can relate to and see that this is not magic, essentially, but with simple tools like that, we can go and actually have a kind of rather important contribution, in my opinion. Okay. I see that I'm running a little bit up, so I will go a little bit fast. Now what we can do is, we have these exact approaches. I already mentioned that this is still fairly limited in what we can do. I mean, this is not, we didn't stretch very far. So if you would know about how to do these models, and if you had a big server, you could probably extend these results to go up to more points and maybe higher dimensions, I don't know. But we didn't push that very hard. Yeah. So these results are obtained on a fairly, let's say, standard laptop. No cluster involved here or whatever. What you could do is we could say, okay, if I'm willing to give up on exact optimization and I just want to optimize and see how far I can get, you can just run Gurobi and interrupt it after some time, and then you will have typically Gurobi will give you an upper bound and give you a lower bound. And then you know that, okay, your optimal point set will be somewhere between these bounds. And what we can see is that even the upper bound is typically, also for a larger number of points, far below like this kind of reference set of the Fibonacci that is there before. But okay. Then there's stuff we can do. I will introduce a few more techniques in a second. But let me also just mention that now that we have this model, you can also say, hey, but in reality, I mean, yes, there's Cox-Malavka inequality, and there's a reason to study these kind of rectangles that are anchored in the origin. But what happens, I mean, what I really care about is arbitrary rectangles. That's the so-called extreme discrepancy, is when we want this kind of difference or this approximation of the volume by the fraction of points to be good for every possible kind of upper right corner, lower left corner. We can just use our NLP and just change slightly kind of the model, and then we can optimize over that. We get results. Here we did it for up to 10 points, for example, just to see and to demonstrate that it's another optimization problem that you could look at and where we know how to tackle it essentially. You could also say, and this is something that's very interesting for practice, that you say, okay, let's stick to these kind of corners, but because I'm maybe energy or inverse of energy, I don't know really how to model it. So let's look at all possible kind of corners in which we would anchor the rectangles, and then measure for these kind of rectangles, all of them simultaneously. That's what we call the multi-corner discrepancy. And there was another big surprise is that if you go and you optimize the placement of the points, not only for these rectangles that are anchored in the lower left, but also those that are anchored in any other kind of corner of the hypercube, then the overhead in the terms of discrepancy is extremely small. And these point sets, these green ones, like where we optimize for all of these, I believe them to be for practice much more relevant. If you do a design of experiment for real world problem, I don't believe that this star discrepancy, like this the star discrepancy, the original star discrepancy is what matters, but actually you should at least look at this kind of multi-corner. And what we show here is that the overhead is fairly small. And that I think that is, I mean, to us, it was surprising. To all the experts we have talked to, it was surprising. And again, I believe there's so much to be done and to be explored that I'm happy to be given a chance to present this topic to you, because I always hope to find people who get as excited about it as I am. Okay, so here's another approach. If you want to go to much higher not much, but higher dimensions like 5, 6, 7, 8, 9, whatever, there's another approach that we tried, and this is based on subset selection. So what we do here, let's say we want to in 5D, and we want to place 80 points or 120 points or 300 points. What we will do is we will take a larger set and then just subset select from this set. For example, here, like the 20 points out of this set that minimize the discrepancy. And we got some fairly good results with that. This is how we started essentially before we realized how to optimize. There's some papers around doing that, either exactly, this is the first paper, or then later we also introduced some heuristics to grow in the number of points and the number of dimensions that we can tackle. Okay, so we had these results, we presented them, and then people got excited about it. And then it was funny moment for us is when GNNs entered the scene, so graph neural networks. So now out of a sudden machine learning people got interested, and they say, hey, what you guys are doing with optimization, let's take the point sets that that Carola and Francois and Rusch and Catherine have computed, and let's train a graph neural network to compute these points, to place them. So why not? I mean, now we use machine learning for all sorts of things, so why not use machine learning for a low discrepancy point set? And this is the paper that was published in the Proceedings of National Academy of Science. And what they showed, now this is a very complex graph, but what they show here, this is, again, I'm sticking here to 2D case. You see here the Fibonacci, kind of the reference set. And in orange is what you see from this paper that was published. Here, these are the orange points. So you see that, so what they could show is that they could go, I mean, remember we had up to 20 points, right? And what they showed is essentially that with GNNs, they could extend, they could find constructions that have much, much lower discrepancy than the reference Fibonacci sequence. And so this got them a PNAS paper, which I think quite high visibility. And in parallel, we were also extending our approach, and we got these red points, which you see, I think, still much better than actually what they had shown. And the funny thing is that for us, I mean, what they use with heavy machine learning, kind of these graph neural networks, for us, we do very simple, again, we use our NLP models, essentially, and we get within seconds these kind of red points here. And yeah, so the cool thing is that out of a sudden now there's momentum. Yeah, people get excited about it. And I'm actually quite happy that there are different groups working on that and trying to push the limits of what we can do to find constructions with low discrepancy. And maybe just very quickly how we do that for us. Let me check the time. Maybe I should skip that. I should skip that because I think we are running out of time. I'm happy to explain how we do that. Essentially, we split the problem into two. We first kind of fix the relative order of the points, and then we see them as kind of a permutation. We fix that, and then we only allow the points essentially to move within a certain range so that they maintain this relative order to each other. And then out of a sudden it becomes an easier optimization problem, and that we can solve essentially using our NLP models. So this optimization with respect to a fixed order is extremely easy. What we now only need to understand is essentially how should we fix this relative order. And this is a problem where I mean, if anyone's interested in working on these kind of questions, I'd be more than happy to explore and to explain what we know and what we don't know. There's much more we don't know than what we know. There's so much room for improvement and so much room for understanding. And I mean, we are working on that, but we are actually, I think, happy for everyone coming in and bringing in their own ideas, very excited to collaborate. And just again, to go back to this inverse discrepancy, if you see what they have done with the GNNs, 500 points, for us, we get the same value with a little bit more than 300 points. And again, if you think of every evaluation to take like whatever significant time, then these kind of improvements, they are really, 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 I think, for practical purposes, they can be really, really important. Okay. Just, I mean, now I will rush, but now just to say that we also have kind of heuristic versions. This is joint work with Martin, the postdoc, where we are currently extending kind of an optimal approach. We're giving up on exact optimization. We use some kind of heuristics, and we do get pretty good results compared to this kind of reference point sets. And this in running time, that is scales pretty nicely. And we can do that also for this multi-corner, like the one where we don't look only at the ones anchored in 0, 0. And we can also do that in higher dimensions and so on and so on and so on. Okay, I will skip this slide. We do have some other approaches. I think key takeaways is, I think that, so we did this work and we had some rather unexpected structural insight, and it really kind of boosted motivation to look at this 100-year-old, I mean, the first publications about this topic date back to 1960, I think, like 16, more than 100 years ago. And I think that this kind of first results really, motivated and said, okay, let's look at it as an optimization problem. And we had some other kind of nice results, like on the side, like the small overhead and so on. Some other thing that was rather unexpected is that we could use other norms than the infinity norm to get good point sets and so on. And why is it so unexpected? And I'd like to show this picture because I believe that we look into this 100-year-old problem, but we came in with our, let's say, computer science or optimization point of view, and not with this asymptotic mathematical view. And we're looking at the same problem, but from a different angle. I think we could just see something that other people could not see. And maybe this is a key message I hope to take away also for maybe students attending this presentation, is that sometimes it's not about like very heavy technical contributions, but sometimes it's more like the idea that matters. I think this is a really beautiful example where the idea itself kind of had so much impact.